Time today, but still I would like to introduce Boris Hanin for his last lecture about neural networks and deep learning. So it was a great series, and today is concluding high note, which is nodal problems in random ReLU nets.
Well, okay, thank you. So first of all, maybe, because I'm sure I'm going to forget at the end, let me thank Giovanni and company for inviting me at all to visit. It's been fun to get to know you all. So I thought since today is Friday, and since it's Giovanni after all, it's good to have at least one lecture on nodal problems. Okay, so maybe for those of you that don't know, in a previous life, I kind of did mathematical physics and spectral theory, and I spent quite a lot of time thinking about zero sets, i.e. nodal sets of random functions, and that's how I originally met Giovanni and his team. They were also working on similar subjects. So it turns out there's some kind of fun nodal problems with ReLU networks as well. So let me start. I'm going to do my best to draw good pictures in this particular talk. Okay, so let me just remind you for a moment of the notation, in part because I sometimes switch normalization on you and so on. So it's good to just fix ideas. Okay, so I'm going to take for this entire lecture my nonlinearity to be ReLU, which I remind you is just the maximum of 0 in the input. And okay, ReLU is the most popular nonlinearity in practice, so I don't feel too bad restricting myself to this case. And so what did a ReLU network look like? Okay, I'm going to add back in the biases. Since I usually didn't talk about them, let me just remind you. So you start with an input in Rn0. Okay, and then we process it through a sequence of hidden layers. So we have the pre-activations in the first layer. And okay, here I restore to its full glory the fully connected network. You have weights and biases. So you take an affine transformation to get to Rn1. I'm just reminding you of all these things, but I'm going to use all this notation, so may as well. Right? In the second layer, we do almost the same thing, but we take an affine transformation of your nonlinearity, which in this case is ReLU, applied to the pre-activations in the first layer. And you go to Rn2. And you keep doing this till your heart is content, or until you've run out of memory on your computer, whatever comes sooner. Right? And the output of the network was just an affine transform of the final hidden layer. So let me write it down. Okay, sigma of ZL of x plus BL plus 1. Very good. All right, so very nice. So in general, we have been talking about the fact that neural networks are nonlinear functions. So what did we mean, again, by nonlinear? Well, when I mean nonlinear, I always mean nonlinear in their parameters, the W's and the B's. And for ReLU nets in particular, you might ask, what kinds of functions do you get when you have a ReLU network? Okay, so maybe the starting point for this whole presentation, which I've mentioned several times, but I just want to reiterate because it's kind of the main point today. Right, for any setting of parameters, for any W's and B's, the function you get, so let me call this theta, the map from inputs x to outputs at this particular value of theta, is always, well, what is it? Okay, it's continuous and it's piecewise linear. Okay, why is that? Well, because it's a composition of things that are continuous and piecewise linear. Certainly affine transformations are continuous and piecewise linear, and so is the ReLU itself.
Should theta be indexed by L here?
Ooh.
Or is it all the...
Sorry. Oh, yeah. Sorry, I understand the question. Yeah, it's all of them. It's all the parameters. Sorry. Thank you. Yes. Yeah, so I'm saying if you set all the weights and biases everywhere in the network and you just freeze them and you look at the map from x's to outputs, it's always continuous. Continuous and piecewise linear. Okay, if you want to be more careful about it, you might say that the gradient of this map is piecewise constant. That's another way of thinking about it. Okay, and really the goal for the presentation today is to try to understand how complex or how interesting of a piecewise linear function do you get. Okay, so the goal is the following. Study the shape, the size, the number, and so on of the linear pieces. Okay, I say it's piecewise linear, so I want to know things like how many pieces does it have? Okay, so these will turn into nodal problems. So let me just stop for 1 second, make sure this is okay. Is that kind of clear what I'm doing? I'm about to do a bunch of examples and give you some specific theorems and so on, but at least like at a high level. Everyone seems either too tired because it's Friday or genuinely happy or neither. Okay, fine. So here's my plan. I want to make a kind of contrast between extremal deterministic results. You might ask, what's the biggest number of pieces you could possibly get for any setting of your parameters theta? What's the smallest number of pieces? These are kind of things like extremal combinatorics. Versus what do you get on average? So the main part of the presentation is going to be to take the weights and biases to be IID random and ask what's the typical behavior. And we'll see they're rather different. Okay, but I want to start with the deterministic results, just to kind of understand what might be possible when things are random. Deterministic results. Okay, and it's kind of a classic thing in nodal sets. Sometimes you can have functions that have very weird behavior, but they either have very low probability or probability 0. And so you'd like to know what's the typical behavior. That's the kind of thing we're driving towards. Okay, so deterministic results. Okay, so here, let me see how many theorems I want to present. I think just one. Note that's a lie. I'm going to present 2 theorems, okay, but they're both really quick. But it's just to give us a sense of what kind of functions we're supposed to be getting. Okay, so theorem number 1, I'm not going to attribute it to anyone because I think it's too trivial. I think everybody knew it, or everyone pretends to have known it at least. Okay, so first of all, the number of pieces is always bounded between 1 and 2 to the number of neurons. And now, I should have probably said, I'm going to fix the output dimension to be 1 for this presentation. It doesn't much matter. It just makes my life easier for drawing the graph of a function. Okay, so it's some function from Rn0 to R in the way I'm normalizing things. And I'm saying the number of different pieces you have in your piecewise linear definition can in principle be 1. And it's no more than 2 to the number of hidden layer neurons that you have, number of times you applied sigma. Okay, so let's do the proof. The proof is simple, but okay, it's kind of nice. Okay, so for the lower bound, okay, maybe someone in the audience can provide the proof. What's the proof that you could have a function that has just one piece on which it's defined? Yeah, okay, so how do I set that up?
Would you mind repeating the question?
So I'd like a proof of the lower bound that you can actually get down to one piece.
Set all biases the same, all weights the same, so you have only one.
Well, not if you have many layers. Right. Is that my phone? Awkward.
I think I said only in the first layer everything equal, and in the next layers the bias is to minus infinity, so they always return the linear part.
Okay, so okay, let me channel. I'm sorry, you're Andrew.
Yes.
Okay, that's what I thought. My inner Andrew. So why not just take the final layer weights and biases to be 0? Okay, then I just get the 0 function. And this function is constant. It's defined on one piece. Okay, that's the proof of the lower bound. You could also take the biases to be more and more negative. There are lots of ways you can do it. But I'm saying, like, you can really achieve that your function is not complicated at all. It's not saying much, but just an observation. Okay, so how are we supposed to think about the upper bound? Why can you only have 2 to the number of neurons? So maybe someone in the audience has a sense. I'm about to write the proof. It's just a couple lines. It's like a good mental exercise.
Each can either activate or not activate.
Ah, excellent. Okay, indeed. So the key observation, I'm about to write it carefully in a moment, is just if you were to tell me a priori for every time you apply sigma, is it on or off? Like, are you setting the component to 0 or are you just letting it pass through? If you were to tell me that, then the function you have is just itself an affine transformation, because it's just a composition of affine maps. Once you remove the nonlinearities by setting the sigma to 0 or not, that's kind of all there is. And there's only 2 to the number of sigma's ways of doing that. Okay, it's potentially a large number, but it's an upper bound. Okay, so let me write that carefully. So for the upper bound, we can say like this. So suppose somebody gives you a sign pattern or a mask or an activation pattern, whatever. I'm going to call it epsilon. So epsilon is for every neuron in the network. So for each neuron in layer L and for every L, I'm going to give you a number that's either plus or minus 1, i.e. it's just going to be telling me if the neuron is on or off. So little l goes from 1 up to capital L, I goes from 1 up to NL. So, and each of these, this is a element of plus minus 1 to the number of neurons that I have. So for every neuron, I tell you plus 1 it's on, minus 1 it's off. And I'm just going to write down what I just told you, right? So consider the set of inputs, so I'll call it R sub epsilon for region. So this is the set of x's in Rn0, such that the sign of each neuron at this x is what I tell you, epsilon Li, for all I and L. Okay, so this is the set of inputs that achieves a given kind of activation pattern in your network. Okay, so then I want to make two claims. So then, first of all, your neural network function, ZL plus 1 of dot, restricted to R sub epsilon, is affine, for the reasons that I just said. It's the same affine function on this whole set. Again, because if I tell you which neurons are on and which neurons are off, you can just remove all the sigmas. And sometimes you replace it by 0, and sometimes you replace it by the identity. So you get a particular affine function. Okay, good. So this is like a piece of definition. And this is what we need to check. Okay, and this set R sub epsilon is convex. So it's really a partition into convex sets. And on each of these convex sets, your neural network is an affine function. Okay, it's not some weird, disconnected, kind of like crazy thing. Okay, so this is not completely obvious, so let me check this second point. Okay, so indeed, so how do you know that this thing is convex? Well, okay, it's not completely obvious at first, but it's completely obvious in retrospect, like all things. So R epsilon is nothing more than the intersection over all the neurons in your network, and L of a set that I'll call, what did I call it? R epsilon Li. Okay, where this R epsilon Li is the set of inputs, as you can imagine, where the sign of the ith neuron is what it should be, is epsilon Li. Okay, so, well, that's just kind of the definition of this region. It's the intersection of all the correct activation patterns. And now the point, like almost all arguments in the neural network, is you have to go one layer at a time and try to understand what's going on. Okay, so let's try to understand what happens in the first layer. Okay, so note, right, so the map x maps to z1 of x is, just by definition, it's an affine map. Right, here it is staring you in the face. I wrote it up here for a reason. We see it, just x. There's no sigmas yet at all. Okay, so therefore, since it's an affine map, what do we know? What are each of these spaces, regions R epsilon 1 sub I? When you look at the neurons in the first layer and you ask when they're on and off, how would you describe this region? Just to see if anyone is actually still listening. If everyone's thinking about soccer, also known as football in some parts of the world, I hear. So, right, so this is the set of points. This is the set of x such that WL plus 1 dot x plus B, 1 I, the sign of this is either plus or minus 1. How do you describe such a collection of points?
They lie one on the other side? No.
Yeah, exactly. It's a half space.
Yeah, it's a half space.
Exactly. Okay, very good. But half space is what we build convex sets out of, right? Okay, good. So this is a half space. There's a half space. Okay, very good. But in the intersection of convex sets, half space or convex sets, is still convex. Right? So therefore, what I'll call R1, which is just the intersection, and I goes from 1 up to N1 of these R epsilon 1i's, is convex. Okay, so that's good. So we're not quite there yet, but we showed that when L equals 1, we get a convex set. It's like where some neurons in the first layer are either on or off. Okay, and now how do I proceed? There's only one line to continue the proof. But maybe someone can supply the line. Say again? Okay, good, but like my starting point for the induction was that the map was affine. I needed that like. Now I'd like to go to layer number 2, and definitely the map from x to z2 of x is not affine in general. I mean, it's got pieces, but okay, I think I heard the right answer. But look, if you tell me, like on this space, on this particular region, if you tell me which neurons are on or off in the first layer, the map to the second layer is affine, right? And the map from x restricted to lie in R1 down to z2 of x is affine. Because I've just linearized the first layer of the network. I've told you which neurons are on and off. And now I can repeat the argument. Now I know this map is affine. Therefore, on this set, all of the R2 epsilon i's are half spaces intersected with this set. And therefore, their intersection is convex. And okay, you keep going. That's the end of the proof. Okay, so again, the number, this 2 to the n1 plus nl, is just the number of possible R epsilons that you get. Okay, that's the proof. So let me put this up, and then I'll pause and see if people have questions. I'm about to kind of get to the place where I can draw some pictures, but I thought it's good to just start with some examples and some kind of deterministic properties like this. Okay, is this okay? Are you happy, Giovanni? Okay, Giovanni's always happy. Understood. Good. Okay, so fine. So let me make one final deterministic comment, because we're going to come back to it, and it's a beautiful kind of paper in the history of neural networks. So it turns out that the upper bound, unlike the lower bound, is not always achievable. You cannot always have an exponential number of pieces depending on the number of neurons in your network, but sometimes you can. Okay, so let me give you a theorem of Telgarsky, which shows that you can have an exponential number of pieces. It's a very simple construction, okay, and it'll bring us nicely full circle to the first day, which is now receded into the mists of time. But on Monday, I told you I had my favorite neural network. Okay, so let me recall it. Recall the following neural network, or just define the following neural network. Okay, so I'm going to define a map. X maps to z of x is a particular neural network, and it's this one. You start with x. You have 1, 1 as your weights. You have 0 minus a half. Then you have 2, negative 4. And you have 0 bias. And all of these were sigmas. Okay, this is x, and this is z of x. And recall that the function this thing computed, we checked this on the first day, was the function which was like the hat function. Okay, maybe I take a different color just because, well, why not? Right, this was the function that was 0 outside of 0, 1, and then went up to the level 1, and then came back down. This was the function z of x. Okay, so Telgarsky's theorem says the following. It says you can get an exponential number of pieces in your piecewise linear function if you compose this function with itself enough times. Okay, so define zk of x to just be z composed with itself k times. K times applied to x. Okay, that's a perfectly sensible function. So then, this is now, the input dimension is 1. The output dimension is 1. So I have some piecewise linear function, continuous piecewise linear function of one variable. Okay, that's something we can all imagine, but I'll draw it in just a moment. But I claim then the number of pieces in zk, what did I call it, zk, is like 2 to the k plus 1. If you want to, I'll just say it grows like 2 to the k. Allow me to write that. Okay, so let's see that, and then I'll try to make some comments about what's going on. The proof is just a picture. It's very simple. Right? So when k equals 1, when you would just have one of these functions, we already know we got this. Okay, this is 0. This is 1. Okay, so now what happens when k equals 2? What's the graph of this function? Okay, what happens when you compose this with itself? Say again, please? Okay, yeah, precisely, exactly. That's the right way of saying it. So you see, this map takes the unit interval and maps it in the output also to the unit interval. But it does it twice, right? It really maps the interval 0, a half to the unit interval, and then a half 1 back to the unit interval. So really what you're going to have is you'll still have 0 and 1, but now you'll have actually 1 hat for every copy of the unit interval you got in the output of the first map. Okay, so this is a half, and this is a quarter, and this is 3/4. Okay, I'm not going to draw it any more precisely than that in general. Okay, so, and then what happens for general k? Well, same exact thing, right? Every time you used to have a copy of the unit interval, you now divide it in half, and you get a new copy of the unit interval. So, okay, for lack of better picture drawing skills, you're still going to have 0 and 1, but now you'll have 2 to the k sawtooths, if you want to call them that. This is like 2 to the k, like, peaks. Okay, and maybe it's 2 to the k minus 1. Hold on. So here I had 1 peak. Okay, so if you want to be very precise, 2 to the k minus 1 peaks. Right, so that's 1 peak. Here I had 2 peaks. In general, I have 2 to the k minus 1 peaks. Okay, so, and you can see that this network, right, so zk has order of k neurons. Right, because, each one of these little pieces of zk has order 1 neurons, and we have k copies of them. But has 2 to the k pieces. All right, because each one of these peaks, in fact, is described by 2 pieces if you want. Okay, and if you count these ones out here, maybe 2 to the k plus 1. It doesn't matter. They're just kind of constants that are floating about. Okay, so this is meant to be an illustration, so sometimes called the expressive power of depth. Okay, this goes back to the fact that machine learning people like funny terms like this. Deeper networks can express compactly more interesting functions. Right, so if you go back to the very first lecture, if you wanted to have 2 to the k pieces in a situation where you only had 1 hidden layer, you would need 2 to the k neurons. That's what we showed, right? If you just have 1 layer, every neuron can only turn on and off once. And so this was taken at the time, although it's kind of, not as popular a point of view these days, that deeper networks express more rich functions with a smaller number of neurons. Okay, that was kind of supposed to be the point. Okay, and the basic question that I'm interested in this presentation, from my point of view, whenever you have a theorem which says that the number of pieces can be 1 or plus infinity, basically, okay, 2 to the number of neurons is some crazy number. The question is, what happens on average? Okay, so what happens when theta is random? Okay, this is almost a nodal set problem. It'll be a nodal set problem exactly in just a minute. Okay, so, just intuitively, if you just take a particular neural network, let's say you take this network, with this building block, you take it k times, take random weights and biases on it. On average, who thinks you're closer to 1 piece? Who thinks you're closer to 2 to the k pieces? Who has any thoughts whatsoever?
There's something in the middle, because the effective number of parameters is still the number of neurons of each layer times the number of layers. So in very unlikely cases, it is going to be exponential, and on average, it is proportional to the product of the 2 parameters, no?
Well,
polynomial.
No one said you can get every function with 2 to the k pieces, right? That would be an impossibility for parameter counting reasons. But the statement is of the form, there exists a function with exponentially many pieces that you can write down compactly in this way. And so, it's kind of like, well, if there exists one, sounds like maybe there's a lot of them. I don't know. So that was kind of part of the motivation for asking these randomized questions. Yeah, please.
You're asking entity or absolute continuity of the tokens?
Say again, please.
What type of density am I thinking for the...
Oh, so well, I'll be specific in a second, but just add initialization. You just initialize the W's and B's, IID Gaussian.
Because if it is distributed over a prospect that something absolutely continuous, I would think that the changes are going to come very rarely, because it's it needs to hit very specific spaces. So I would think that's
Well, sort of, but if you're in a situation where you start to build up these pieces, right? The picture is, and some neuron somewhere in the network sees this. If its bias is anywhere between 0 and 1, it's going to cut all the previous pieces into new regions, right? So I mean, it's a plausible intuition, but it's not. What I'm saying it's not 1,000% clear. Okay, I guess it's never 1,000% clear, but you know what I mean. Okay, so that led me to work with my longtime collaborator, David Rolnick, on these kind of problems. So let me start in the simplest possible case, the case where the input dimension is 1. Okay, here you can really draw the function, just a function from R to R, right? You just have univariate ReLU networks, univariate ReLU nets, and one way or another, the function you get is going to look something like this. It's going to have some number of pieces, I don't know, whatever. That's going to be my random function. My question is, how do you control the number of pieces? Okay, so recall, again from the first lecture, that if we had one layer, if capital L equals 1, right, so then the network looks like what? Right, I'm just writing it down. Z2 of x and theta is just the bias of the output plus the sum over the hidden layer neurons, W2I sigma of W1I x plus B1I. Right, and it has, at most, in fact, generically has exactly N1 breakpoints. Okay, for me, a breakpoint is just one of these points where the slope changes. But every neuron can turn on and off exactly once, and typically does turn on and off exactly once. So you get n breakpoints. So for one-layer networks, you have basically a deterministic answer. If you were to choose the B's and W's at random with probability 1, you're going to have a constant number of pieces. You'll have n1 plus 1 pieces. That's how it is. And B, you're very far from this 2 to the n1 number. Okay, so for one-layer networks, you're going to have fewer of them. And the question really is, what happens for deeper networks? Okay, that's what this theorem is about. I think it's safe to go back to this board. But I'll erase from here. Okay, very good. So while I'm erasing, you should try to guess what the theorem is going to say. I think that's, okay. I'm not going to say it's my favorite game, but it's a game. Yeah?
Does it sort of have to count the changes of size on average?
Yeah?
Okay, the way I think about it is that you have to count the number of changes of size. So
Yeah.
it would be 2 to the k minus 1, I mean 1/2.
Okay. That's actually, so your conjecture is it's not going to grow like the maximum. It's going to grow exponentially with a smaller exponent. That's what I thought too. That's really what I suspected was going to be true when I started doing this. And that turns out to be horribly wrong, but I'm not really blaming you. It's just, I think, kind of a natural thing to imagine. It's just not the case, but okay. So here's the theorem, or a theorem. Okay, so this is something I did, like I said, with David Rolnick. It was really great. He's now in computer science at McGill. Okay, so suppose we initialize like we do in practice. So now I'm going to answer Arturo's question. So WLIJ, our Gaussian mean 0, variance 2 divided by the width of the previous hidden layer. I didn't really explain this, but you need the 2 because the ReLU kills you half the time. Okay, this is just the unique right thing to do, as you'll see from the proof. and your biases B, L, I are Gaussian, mean 0, some variance CB. It doesn't really matter, but I do need CB to be positive. Okay, so then the theorem is the following. So then, the expected number of pieces in an interval I, so for any I, it doesn't have to be an interval, but it may as well be, is less than or equal to, there's a universal constant, independent of everything, times the length of the interval I, times the number of neurons. Okay? It does not care at all about how the neurons are arranged. The neurons could all be in one layer. They could be in different layers. You always get that you just get every neuron appears order 1 times in this right-hand side. Now, I'm about to prove this for you. But I was so sure this result was wrong when I thought I proved it that I had to simulate it. And I learned that my intuition was bad. Okay, is it clear what I'm trying to say? This is now very close to a nodal problem, and it's going to become exactly a nodal problem in a second. Yeah?
Because here the bias is not to be 0. Right?
Yes.
And I was thinking about the situation when biases are equal to 0.
Yes.
So is there, in this case, just some completely finished, or is it just...
Yes, so when the bias, so it's not totally obvious, but the fact is when the biases are exactly 0 and your input dimension is 1, the only function you can get always looks like this. It has exactly 2 pieces. And that's basically because when all the biases are 0, the neurons can only turn on and off at 0. They all turn on and off at the same place. So it's kind of not an interesting, yeah. But save that question for the multidimensional case. Okay, it's quite interesting there, and the answer there is I don't know. Okay, a little sad, but that's how it is. Okay, so I want to sketch for you the proof of this theorem. One of the reasons I'm really excited to sketch the proof is that I get to tell you what I think is one of my absolute favorite theorems in all of mathematics, something called the co-area formula, which anyone who's worked on nodal problems either knows and hates or knows and loves. Okay, very good. So let's do the proof. All right, so first of all, the number of pieces that intersect your interval I that you have, I claim is bounded above by the following. So I'm going to sum up over all the neurons in the network. I goes from 1 up to NL. And I'm going to count the number of times there's some input x in this interval I'm interested in such that the pre-activation of this neuron is 0. So I'm going to write it this way. Excuse my new notation. I'm going to write ZL tilde of x is equal to minus the bias at the neuron. And I've just introduced a piece of notation which will be useful to me. I'm just writing the pre-activation as ZL tilde of x plus the bias. So I'm just calling with a tilde the thing you get before you add the b. Okay, so let me just pause for a moment and explain why this is the case. So you know, if you're at a point x where, sorry, let me do it this way. So if you're in an interval of x's, so I have some interval I prime, and as I move through this interval, none of the neurons, their pre-activation crosses 0, right? Where z tilde li of x is equal to minus bi, that's exactly where the pre-activation is 0. So that means that for every neuron everywhere in the network, you're either strictly positive or strictly negative, the pre-activation of that neuron. And that means that your neuron is either on or off for that whole interval. Okay, so that's why you get this upper bound. So that means that everywhere in this interval I prime, your entire neural network is linear. There are no breakpoints there at all. So you can only get a breakpoint when a neuron turns from on to off, and you see that that's exactly a nodal problem. You know, you need to count the number of times that ZLI of x equals 0, i.e. ZIL tilde of x is equal to minus BIL. Okay, so that's the first upper bound, and very good. So what do I actually have to convince you of? I have to convince you of the following fact. So when I take the expectation of this, okay, it gleefully goes through all these sums. I need to compute the expectation of this. So I need to just convince you that every neuron in the network only has, on average, order 1 sign changes for its pre-activation. Okay, in any interval. And so that's going to be it. So that's my goal. That's what I need to show you. So let me give a name to this initialization. So I secretly already showed you this calculation, but I didn't tell you about it. Okay, so this initialization, the reason it's kind of used in practice is the following is true. So the expectation for any neuron of the gradient of the neuron with respect to x, okay, here it's just the partial derivative, at every point is exactly equal to 1. Okay, so this is true for every x, for every I, and for every L. So in other words, this is the initialization people use in practice precisely because it ensures that neurons aren't like constant functions and they're not oscillating wildly. Okay, so this calculation actually comes down to that product of linear random matrices I did for you before, but it's not obvious that it does. So I'll leave it to you as a fun exercise to check this. This is pretty easy to show. Okay, very good. So how am I going to use this? Well, let me first give you the intuition, and then I'll give you the actual derivation. Right? What does this tell you? So this tells you that, you know, the B doesn't depend on X. And so I may as well put a tilde here. So here I am. Here's the input X. And now I'm drawing for you, you know, the function Z tilde Li of X. Okay, it's some function. And what you know about this function, the most important thing you know, is that its gradients are not too big. That's what this estimate is telling you. Okay, but if its gradients aren't too big, it means it can't oscillate up and down wildly. But that means when you just draw a generic level, like minus BLI, maybe that's a nice level to draw, you should only be able to intersect it O of 1 times. Okay, that's the basic intuition. So the only subtlety for making this work is that nothing excludes a function that just oscillates rapidly but with small scale. Right? That's in principle possible. Here the gradient can still be plus minus 1, let's say, but it goes up and down. But here you're very unlikely to actually choose this level to cut with. That's what's going to save you. Okay, so this is kind of the intuitive picture, but now let me give you the exact thing. Yeah.
X is 1 dimension.
Yeah, so for now I'm doing everything in input dimension 1.
So the gradient there, what is it?
Sorry, just the derivative, d by dx. It's true in any number of dimensions, so I wrote it, but yes. Yeah, I'm just saying, like, you can't have wild slopes, and that's all you're going to need when you do. Okay. Very good. So I erase. I continue.
That requires the Gaussian?
No, it does not require the Gaussianity at all. It just requires mean 0 and this variance, and that's it. I just do Gaussian because that's what I do. All right. So how do you? So you need an upper bound on the following object, right? The expectation of the number of x's in your interval I such that z tilde Li of x is equal to minus BLI. Okay, so this is strictly easier than most nodal problems because you're asking about a random level. That really helps a lot. Okay, so how do you get a formula for this? Well, you have to recall the co-area formula. So recall called the co-area formula. And it's kind of a particularly beautiful result in geometric measure theory that generalizes to quite a large extent kind of change of variable formulas. And it works on manifolds. It just works in basically, well, I don't want to say full generality. There are even more general results than what I'll say, but it doesn't matter. Okay, so it goes like this. So suppose, maybe I'll write it here. Okay, so suppose you have a function, psi, that belongs to L1 of Rn. Okay, some integrable function with respect to Lebesgue measure. And you have a function g from Rn to Rm, which is Lipschitz. Okay, m here is less than or equal to n. Okay, so we're basically going to use g as a change of variables, kind of. So I'm going to draw my Rn up here. Here's Rn, and here's Rm. And this is the map G. Okay, so I want to do some kind of integral of psi over Rn, and I want to write it as an integral first over Rm, and then for every value t down in Rm, I want to write it as an integral then over the preimage, G inverse of t. Okay, so I'm about to do that. No one can stop me.
And n is greater than n.
N is greater than or equal to, but they can be equal. Yeah. So the beauty of this theorem, one of the reasons I like it so much, is that you're basically using a function that has almost no regularity, like a Lipschitz function, to do your change of variables. You don't need C1. You don't need anything like that. It's just a fairly low regularity change of variables, which is super useful. Okay, so what do we get? So then, if you want to integrate over Rn, your function psi of x, but here I have to integrate it with respect to the right measure. So the norm of the Jacobian of g of x dx. Okay, so what the heck is this thing? This is the square root of the determinant of the Jacobian of G transpose. Okay, it's just the usual thing that comes up in the change of variable formula. Okay, and here's where I basically use Lipschitz. You know, if you're a Lipschitz function, your Jacobian is defined almost everywhere. So this makes sense in a kind of L1 integral. Okay, very good. And what do I get down here? I get my dream. Okay, I get to integrate over Rm. I'm going to integrate dt. And then I'm going to integrate over the fiber, G inverse of t. And I'm going to integrate psi of x over the fiber. And, okay, so here, this was the Lebesgue measure. You can think of it as the n-dimensional Hausdorff measure, if you know what that is. It doesn't matter. It's kind of the natural measure. And there's a natural measure here. This is the n minus m-dimensional Hausdorff measure of x. Okay, this is just the natural induced measure on this level set of G that you get it almost everywhere. G is almost everywhere regular. Okay, so if you don't know what those words mean, it doesn't matter. I'm just saying there's a beautiful formula like this. You can use it to your heart's content. You don't have to check any hypotheses, really, because basically Federer did it for you. That's what I would say. Okay, so let's use this formula. It's not obvious that we can use it, but okay, we can. So maybe somebody already sees. I'd be impressed, because I never saw this kind of thing. So suppose I give you this formula. This is called the co-area formula. And my goal is to compute this expectation at the top. How am I supposed to use the co-area formula to do this calculation? Anyone see? Kind of exciting. As exciting as the co-area formula can be. I think it's pretty exciting. Also, it's kind of just a beautiful, somehow really hits all the right notes. Okay, so let me do it this way. So I want to compute the expectation up in the top right over there. And so what's random in the top right? Well, the weights are random and the biases are random. Okay, so let me start by integrating out just the bias in this particular neuron. Okay, so note that. If I just tried to integrate out this bias, BLI, of the number of x's in the interval I, such that z tilde li of x, okay, is minus BLI. What do I get? Well, you see, this function z tilde is going to be the function g that I'm using. I'm choosing it to map from R to R. So this thing equals. So what am I doing? Well, I'm integrating over R. That's the B that I'm integrating over. And I get the density of this bias at B. That's kind of the analog of my t variable. And then what's the thing I'm trying to calculate? Well, I'm trying to calculate, if you want to put it this way, it's the integral over z tilde li inverse of minus b, right? This is like the x's, so that z blah, 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 blah equals this thing, of just the function 1, okay, times the counting measure. The zero-dimensional Hausdorff measure is the counting measure, dB. It's quite literally the integral I'm trying to calculate. Okay, it's just a fancy way of saying this is a discrete collection of points. And I'm trying to count up the number of points in such a thing. Okay, it's the zero-dimensional Lebesgue measure, just counting measure. And so, oh my God, you start to jump up and down for joy. That or you put your head down in disgust. But this is exactly this right-hand side. For the Clairaut formula, so I can write it this way. Right? So this is exactly equal to the integral over r. My map is from r to r, so n is equal to m, in fact, in this case. Right? And I get, so what function do I have? My function is just the constant function 1. And I just get the Jacobian, intersected with the interval I. I'm only interested in the x's in I. So I just get the indicator function of the interval I of x. And then what do I get? I get the norm of the gradient of z tilde Li of x dx. Okay, that's what the Clairaut formula gives me. Whew, I did it right. Sometimes I mess it up. Okay, so what we've done is we've integrated out the bias. Okay, but now nothing can stop you from integrating out. Sorry, I lied. I'm a lying liar. Don't listen to me. This is the density of BLI at minus z tilde Li. Sorry, this was my function, psi, that I had. I had that as well. And so this is this at x dx. Okay, whew, now I got it right. Now Giovanni's happy. I think he was happy before too, but he's even more happy, if that was possible. Okay, so now I declare myself basically done. So this is less than or equal to, okay, I can just write this as the integral over I. That's this indicator function. I'm going to keep this here, z tilde Li of x. And here I told you that I had a non-degenerate Gaussian distribution for my biases. Okay, so this is just less than or equal to a universal constant. So I just throw it out, and I get dx. And then finally, you just take the expectation. Finally, you just take the expectation of this plus wherever I wrote this estimate on the gradients, right here, plus that thing, plus the star. So that's the end of the proof. So I just wanted to show you the proof's really not that bad. I wrote it in just a couple of lines. And you really see what's going on, right? The number of crossings of a given level has two contributions. There's how much z is oscillating. That's this term right here. And then there's how likely you are to cut the level at that point. Right? And so those are the two pictures I was kind of trying to draw before, but this is the precise version of it. So let me just stop for 1 second and take comments or questions, because I want to draw some pictures in higher dimensions, since this is kind of the end of the one-dimensional story.
Where are the ends?
So remember, I did this for every neuron. So in the beginning of this proof, I showed you that the expectation of each sum end is bounded by the length of I. Right? And then you have to sum up over all the neurons. So yeah, I just didn't write that, but that's right.
This suggests that the function is sort of like a little bit less than Lipschitz.
Yeah, so it's an interesting question. Okay, so let me do this. I'm going to just leave this up. I'm going to do some erasing. Let me actually end this section with some open problems, partly to address your question, but partly because, you know, the people must be pleased, and mathematicians are only pleased when they have open problems. Okay, so much for this proof. Pretty easy. It's like a cat's rice formula for a random level, which is even easier than the usual thing. So let me make some remarks and some open problems. So open problem number 1 is we saw that the variance of the number of pieces when L equals 1 is 0. With probability 1, you got exactly n1 plus 1 pieces. Nobody knows what the variance is in general. Question. Variance for L greater than 1. Okay, but this gets back to your point, Arturo. You see, on average, I told you there aren't very many pieces. But what really happens, okay, I have a conjecture. So I conjecture that the variance is exponential times 5 times L over n. That's my conjecture for the answer. Okay, that's a very precise conjecture. But the point is that when you take really deep and skinny networks, imagine one of the neurons was off, somewhere in a layer that had just one neuron. Then it kind of deletes all the pieces you made before. So usually, when you take one of those really deep, skinny networks, you're going to have like just a couple of pieces. But then sometimes you're going to have this crazy exponential number of pieces. So the variance is going to grow very much as a function of the depth. That's the difference between deep and shallow. You can't see it on the level of the mean. That's what this theorem is trying to tell you. But I don't know how to do the variance, mainly because I'm weak, not because it can't be done. I actually tried embarrassingly hard to do it, and I failed. But I really just didn't find the right approach. I bet it's easy. I bet it's easy.
But does this imply in terms of the real life?
Well, it would suggest that the kind of functions you're starting with are really weird. They're usually very, very, very flat. But sometimes they're very, very spiky. And on average, the number of pieces is exactly what I said it is. I don't know what else to say. Yeah.
One question. So the problem that you raised, you initialized the biases with variance CB.
Yes.
Are there any constraints or expressions for CB as a function of the depth or width that yields some consistency or nice convergence result, or the optimal CB recommendation?
Unclear. I don't quite know how to answer that question. It's a sensible question. In this theorem, the CB is just a constant. But that constant appeared when I estimated the density of the biases. And so,
is it similar to the variance that enters the expression for the weights?
Sort of. Often in practice, people will make the biases zero at initialization. It's just a bad idea for input dimension 1 for the reasons that I said. But yeah. Yes. Exponential of 5 times L over n. Well, okay. So the reason this thing as opposed to some other thing is you saw that the crucial question was, in some sense, how big is the gradient of a neuron? Okay, and what it turns out is that I told you the expectation of the square was 1. But you can actually get the whole distribution using that kind of trick of matrix products. It turns out you slightly modify it. And you get that this thing looks like exponential of a Gaussian with mean minus 5L over 2n and variance 5L over 2n. That's what you got. And basically, like, if you believe that the number of breakpoint scales like the typical scale of this gradient, that's what you expect. It so happens if you square this, then the expectation of this log normal thing is exactly 1. So you don't see the L over n. Well, 5 comes because it's 3 divided by a half minus 1. So yes. Okay. Don't force me to go into that now. Okay. It's a fair question, but there's some reason for the conjecture. Okay. So what else is open? So embarrassingly, the global number of pieces. So I told you about how many pieces lie in an interval. And on the one hand, that's a strong result because it really gives you kind of the density of these pieces. On the other hand, if you take the interval to be all of R, you get a garbage upper bound. You know you can't have more than 2 to the number of neurons. And I actually didn't figure out how to remove that. Okay, so I don't know how to do it. But you could do almost anything you like. You basically have a point process in R. You could study like the length spectrum of this point process. You know, how many pieces are there below a given size, like below a given diameter? You could study almost anything out there. Okay, so let me just say ... because I want to draw some pictures for the higher dimensional thing, unless there are more questions or comments here. Okay, so hopefully Michele is kind of happy. Or at least interested.
Taking the limit with n goes becomes Gaussian computations.
Yeah, but the thing is, your limiting Gaussian process is actually smooth. And so the number of pieces has to go to infinity because your ReLU networks are piecewise linear.
Yeah, sure, but
yeah.
Maybe in this way one can compute this constant and see the exact rate
I mean,
in n.
So again, like at finite size, your network is piecewise linear. I'm trying to calculate the number of pieces. Number of pieces will diverge as the width goes to infinity. And so I'm not sure I've never figured out how to connect it to a really Gaussian calculation. Like in the end, I'll get infinite, okay? Which is not saying that the function's complicated. It just means that it's smooth. You need an infinite number of piecewise linear pieces to get it.
If that's the quantity, it's the derivative of something that is converging to a Gaussian field.
Yeah, that's true. That's why it remains order 1.
Make the 1 over n go part outside. Or the n.
The trouble is your neural network, like your ReLU is not very regular. So you have the Gaussian process result, but it's not clear that you're going to get the Gaussian process result with the derivatives. So you have to be a little careful. So yeah, so it's something that's possible, and I don't know. That's the truth. Yeah. So,
Quantify how much in this case
yes.
convergence is not in C1.
That's right. That's right. Because certainly not in C1. Yeah.
A question about sparsity. So if the result is piecewise linear, instead of storing the entire huge matrix of n L times L weights and biases, you could just store as many slopes and intercepts as the number of jumps. Are there any expressions or algorithms to obtain the piecewise linear function from the given set of weights?
There are, but they scale very poorly with the input dimension. So I'm about to show you that things become more interesting and more crazy when the input dimension is greater or equal to 2. But yeah, it's a fair consideration, indeed. Okay, amazing. So let me go on. I want to draw some pictures when n naught is greater or equal to 2. But for obvious reasons, I'm only going to draw things when n naught is equal to 2. Okay, you will presumably forgive me. So let me start with a simple case, just like we did before, when you have one layer. Okay, not too bad. So and n naught is equal to 2. So I just have 2 neurons. These are the 2 input components, x1 and x2. And I have some neurons in my hidden layer, right? And I have this. And then I have the output. So z2 of x is equal to b2. I'm just rewriting what I had before because, well, I don't know what else to do with my life. I'm just going to keep writing what I have in my notes, plus b1i. Okay, so here's the kind of key observation about one-layer ReLU networks when the input dimension is greater or equal to 2. So when the input dimension was 1, we just had one of these continuous piecewise linear functions, something everyone has seen at some point in their lives, I think. Here you have something slightly different. Okay, so let me introduce a piece of notation, and it's going to help us draw a picture. So let me define H1i to be the nodal set of the ith neuron in layer 1. Okay, so this is the set of x such that z1i of x is equal to 0. Right? We decided that these sets were important precisely because where the neuron turns from on to off, that's where the slope of the function changes. Okay, and then recall, we already had this observation before, H1i are just hyperplanes in Rn0. Okay, they're codimension 1 hyperplanes in Rn0. So this kind of thing has a name. When you have a collection of hyperplanes, let me go up here. When you have a collection of hyperplanes in, well, almost any space, it has a name, it's called a hyperplane arrangement. Anyone heard of hyperplane arrangements? Okay, so it's a thing. It actually comes up in quite a number of settings. It comes up in statistical learning theory. It comes up in combinatorics. It comes up in lots of places. But it has a cool name, so that's, I always like to make connections to classical things. Okay, so let me draw the picture. So here's Rn0. Okay, if you want to be absurdly precise, so here are my hyperplanes. You have H1 H11, H12, H13, and I refuse to draw any more, so that's all you get. Okay, so there's some kind of hyperplanes. This is an arrangement of 3 hyperplanes in the input space. But you have a little more information than just the hyperplane. It's a co-oriented hyperplane arrangement. Okay, this is the side on which the neurons are on. You get a little more information. You know that the neuron turns on and off in some particular direction. Okay, so you can think of this as dividing up the input space into these regions that we were talking about before. And you can kind of give a Hamming code to these regions. Like, in this region, all 3 neurons are on. Right? In this region, the second neuron turns off. In this region, the third neuron turns off. In this region, all the neurons are off. In this region, the third neuron turns on. In this region, the first neuron turns on. And in this region, the third neuron turns off. No, that was a lie. I lied. The second neuron turns. What have I done? Wait. No. Like this. Okay. No. Yes. Sorry. I think I need like this, and then I need 0, 0, 1. Okay, I think I win.
0, 1, 0.
Ah! Thank you. Okay, too difficult to calculate at the board. Okay, my point is you can start to see the combinatorics staring you in the face. Okay, you have some way of partitioning up your input space, and this tells you that here's the linear function you get when all 3 neurons are on. Here's the linear function you get when the first and third neuron are on, and so on and so forth. Okay, so you can start to draw these pictures. And there's a classic theorem, if I can find my eraser. Okay, it's a theorem of Zaslavsky, who studied actually this in much more general context, these hyperplane arrangements. So in this world of hyperplane arrangements, the linear regions or linear pieces I've been talking about have a name. They're called the cells of the hyperplane arrangement. Okay, this hyperplane arrangement has 7 cells, 1, 2, 3, 4, 5, 6, 7. So Zaslavsky's theorem says the following. Zaslavsky, that given any hyperplane arrangement whatsoever, there's an upper bound on the number of cells, but generically you achieve the upper bound. So number of cells in an arrangement of, let's say, I'll keep this notation, n1 hyperplanes in Rn0. That's the kind of situation we're in. I'll write here, is generically, so with probability 1, but away from measure 0 set, is generically given by the following thing. It's the sum on I goes from 0 up to the input dimension of the number of hyperplanes choose I. Okay, it's kind of a beautiful formula. It's not obvious there should be such a nice formula, but there it is. So if you've ever seen Sauer's lemma or anything like that in statistical learning theory, you've seen these kind of things come up for estimating VC dimension. They're really the same kind of argument, ultimately. Okay, so this is basically the complete story of what happens. In one hidden layer, you have continuous piecewise linear functions on your input space, but you can't get every such function. They have to satisfy the property that the jump of the gradient you get when you cross one of these hyperplanes is the same no matter where you cross the hyperplane. Okay, that's the constraint. So it's okay, you might like it or not. It doesn't matter. I just told you what one-layer ReLU networks do. It was a bit harder in 2 dimensions, but it was doable. Okay, enough cups of coffee got you there. But now, here's a question for the peanut gallery, kind of. Okay, question. What does the nodal set look like in the second layer? Okay, just for any layer and any neuron, I can now define the set of points where that thing is 0. What does it look like? I'll give you a minute to think about it, and I'll get a different color, just for fun. What do you think? Okay, so I basically added one extra. Just think of the output of that network as being the neuron I'm interested in. Now I have more layers. Okay, I didn't really finish the sentence. Look like. Right, so just to be clear, this is the set of x's such that z21 of x is 0. Well, okay, so let's think about this together. So what do you know about the map z21 of x over in this region 101?
Selecting the terms in the size from 1 to 1 to 1.
Okay, phenomenal. Can you remind me of your name again? Francesca. Okay, right. I'm going to channel my inner Francesca. Very good. That's right. So this tells you that everywhere over here, the first neuron is on, the second neuron is off, the third neuron is on. Okay, so the function in every one of these cells is actually affine. Okay, the map from X all the way to the second layer. And so you know that the 0 set is going to be a hyperplane. H, 2, 1 is going to look like this. Okay, but this is where the interesting thing comes. When you go from one region to another, the affine function you get changes because some neuron turned on or off. Right? Over here, this is a different affine function. And so what happens is the hyperplane bends every time it hits a neuron boundary. Okay, okay, well, now life is getting more exciting. So I call them bent hyperplanes for this reason. So you get a bent hyperplane. Again, although you can't literally get it in this picture, let me just say much more crazy things can happen in deeper layers. So for example, if I have the next one, it can have a little component that is compact. So H22 can look like this, and then also like this. Nothing stops it from doing that. But and you see, I'm just making a pictorial version of the proof I gave you before for the convexity of the regions. You know, each of these little regions is still convex after I've partitioned things up. But they're kind of like complicated. You start to get more interesting objects. Okay, so now you can ask, now can you describe the geometric properties of this partition? Okay, that's what I think of as like the nodal problems associated to a ReLU network. You can ask things like, how many pieces do you get? You can ask things like, how many vertices do you get? How many pieces do you get of a given size? You know, you can start to ask all the questions one asks when one has a kind of random tessellation or partition into convex sets. It's a kind of a classic subject in especially integrable geometry. Okay, and for me, Zaslavsky's theorem is very much like this observation that you can only have n1 breakpoints in a one-dimensional, one-layer network. There's a deterministic number of pieces when you have only one layer. But the variance is going to grow in deeper networks. Okay, so let me not belabor the point and just tell you that there are several generalizations of the one-dimensional theorem. But maybe let me just state this one. It's also with David Rolnick. Okay, basically, for any cube C inside of Rn0, the expected number of pieces that intersect the cube is bounded above by some constant times the Zaslavsky bound. Okay, times the sum, I goes from 1 up to n0 of n1 plus nl choose I. Okay, so if you're taking all the neurons in your network and you just stack them into a one-layer network, this bound becomes this bound. And so on average, again, you don't get more pieces than you thought you did. Okay, sorry, I should say times the volume of the cube. It's a density result. Okay, but I know nothing again about the variance. It's even harder in this case. And so virtually every question is open. And let me, since I just have a minute or two, tell you about something which was really cool. I wasn't able to solve it, but I had a phenomenal undergrad at Princeton who solved it overnight. So I felt both good and bad. Okay, so I asked the following question. I said, consider the origin in Rn0. Okay, there it is. So with probability 1, the origin doesn't lie on the boundary of one of these regions. It's in the interior. So the question I asked was, just in 2 dimensions, how many sides does the region containing the origin typically have? Okay, so some simulations show that this number, when the number of neurons gets bigger and bigger in your hidden layers, converges to 6. And so the student proved that. Okay, I won't explain the proof, but it's a clever duality argument, basically. So it's, okay. The point is there's lots of kind of interesting things here, I think. But let me kind of emphasize a couple of open problems beyond just the one layer problems or the one input dimension problems. Okay, so here are some things that are open. Okay, so just like before, variances, so I can't help myself, and global number of pieces is open. But here's kind of a funny one, which I think is very much in the spirit of, okay, at least questions I used to be fascinated by. In nodal sets, what's the expected number of connected components of H, L, I? Oops. Don't know. Have no clue. As I said, you can in principle have several connected components. They're not so common, but they happen. So I don't know. I don't know anything, as you now know from these lectures, or I know very little of what I'd like to know. Okay, so let me actually pause for 1 second and see if there are comments or questions about any of this. Yeah.
Was going to have lower bound for the expectation?
I'm trying to remember whether I got lower bounds. I can't remember if we got lower bounds in this paper. The upper bounds were shockingly painful because I think we had a bad approach, honestly. So I wouldn't be surprised if we didn't have lower bounds. I mean, I suspect the lower bounds are on the order of the upper bounds. I mean, just because this is kind of the minimal number you expect, but what do I know? I don't know. Yeah, I'm not sure. Yeah.
Can you put on the activation 0, 1s for the sigmas, if you put them in, you could have access to an arrangement of
Say it one more time, please.
In your picture, you're only calling the activation or non-activation by a sequence of,
Yeah.
of binary things.
Yes.
Could you say something about jointly what happens in some way, because there are going to be many, but in some way to the tendency of activation, non-activation?
Oh, I see. I understand. Yeah.
The tendency of some part of the network being activated, some other not.
Yeah, the short answer is I don't know how to do anything like that. It's a natural question to ask if you're interested in just describing. I think it's kind of a beautiful, just geometric gadget to think about. But like, I don't know much more beyond this, exactly what I presented, essentially. Yeah. So maybe let me say, one of the reasons I was interested in these theorems originally is people said, like I was presenting the Tilgarsky result, deeper networks are better, they're more expressive, they give you better functions. But these theorems show that, in some sense, at least on average, it's just false. And really, like, the fact that deeper networks seem to work better in practice seems to be much more closely related to the fact that deeper networks do something better in the course of optimization. They bias you in some way to learn more parsimonious functions. So it's more about how depth interacts with optimization than like the raw power of the functions you can represent. But it's a little bit of a vague statement. There aren't kind of too many exact theorems in this direction. But that's why I was interested in these problems. And people were a little surprised to get such upper bounds. So, okay, we were kind of happy at the time. But happiness is fleeting and all that. Yes?
Would it be interesting to consider also local questions like the size, volume of the species?
I think so. I mean, and I know very little about it. I mean, we did some numerics. And you get pieces at many scales, as you can kind of imagine. Right? You sort of imagine you're just kind of bringing in one more of these things. And it kind of is more likely to intersect the big ones, but then sometimes we'll kind of like puncture the small ones as well. You know, I don't know, maybe it does this. It can't literally do that. There are topological reasons why that's not possible, but you know what I mean. And so, yeah, we were trying to inductively say what the typical volume is, and we utterly failed. So, but yes, I'd be happy if you tell me the answer. Yeah.
Is the estimates preserved after training?
Yeah, it's a great question. So the short answer is, so if you think about what I used in the proof of that upper bound, I used very little about the distribution of the weights before training. I just needed that the gradients weren't too big. That was the main kind of thing I needed. And so that's how we formulate the theorem, and we don't know how to check that that's true after training, but we just empirically went and checked. And what we found is that even when you really try to learn more regions, like when it helps you to fit the data, it was very hard to get a network to learn many more regions than it started with. That doesn't mean you can't do it, you know, but we made an honest effort and we couldn't. And our reasoning was something like, to make lots of pieces, you have to have a highly oscillatory function. But highly oscillatory functions are unstable in gradient descent. If you happen to get one, you'll differentiate it and you'll get a big gradient and you'll kind of be kicked away. But you know, it's all kind of just words at that point. Yeah, so I'm not sure, but I suspect something like that's true. Yeah.
My question is, this so far looks discrete, and when the objective function is, well, a penalty, well, defined in these regions, quite often it could be non-differentiable. For example, and for a reason, let's say in robust statistics, instead of using the absolute value loss, like the Hewlett, they use the modified one, but it's smooth and zero. So here, this discreteness is related to the fact that we're using the ReLU with a sharp corner. Are there any results on the sort of optimizational superiority of slightly smoother activation functions?
So in some situations in practice, people will smooth out the ReLU. They'll use the GelU or the CellU or other U's. It's not clear that there's anything fundamental about it, honestly, but sometimes it works a little bit better, and that makes the difference in practice. And beyond that, like having a theorem which says this nonlinearity is way better than this nonlinearity is like pretty rare. Because it's unclear kind of in what way that's going to happen, except for some pathological situations. So I don't know of such a result.
But it could be related to the fact that when the networks are deep and wide, that this partitioning is kind of fragmented, that it resembles a smooth function, or are there any other reasons why people go with a standard non-smooth function that is...
It just works the best. I know it's not a satisfying answer, but like if you try a hyperbolic tangent, it just generally won't work as well. So it would be great to have a better explanation than that, but that's just kind of at least where I am for the most part. Yeah. Yeah. Sorry not to be more satisfying. Yeah.
All these random subsets, hyperplanes, again, they don't have any impact on the distribution. You can see them as a random subset.
Well, in the first layer, if you have Gaussian weights, they're... but no, beyond that, it's kind of more complicated. I call them bent hyperplane arrangements just to have some kind of title for them. But, you can kind of imagine why, for example, I don't know how to do the variance things. There's not so much like symmetries to use. And, I mean, nodal sets of piecewise linear functions is like not so easy when you have to study the derivatives at various points. It's like you just don't have much smoothness to work with. On the other hand, they're just piecewise linear, so they're kind of combinatorial. So I think there's just something which is not co-area based, which will do well, and I don't know what that something is. That's kind of my guess. The co-area formula really doesn't seem to generalize very well beyond the kind of expectation here. Yeah. Okay, so there's a bit of time left, but I think this is maybe a natural place to stop. I hope I've kind of convinced you that, okay, there's some interesting mathematical problems in deep learning of various kinds. Some of them are fun and combinatorial. Some of them are fun and something else. So thanks for all the questions and the attention. I really appreciate it.
Is there no more questions, I would like to thank Boris on behalf of all the departments that have been involved this week in this series of lectures. So this has been a fantastic occasion for every one of us. Beautiful lectures.
Thank you.
Extremely interesting, or wide, or broad.